Good to have you in today's class, where we are going to be looking at the concept of valency and oxidation state. When we say valency, we are simply talking about the combining power of an element. So, valency is simply the combining power of an element, or the capacity in which an element uses to combine with other elements to form a compound or a molecule. What about oxidation state? Oxidation state or oxidation number has to do with the valency of the element or the atom plus the charge on the atom. Of course, metals have positive oxidation state, while non-metals have negative oxidation state. When we say positive oxidation state, we are talking about the cations, while the negative oxidation state has to do with what? The anions. Now let's go back to valency. Valency of an atom or an element, just as we said, is the combining power of an element in which it combines with other elements to form a compound or a molecule. So we can know the valency of elements from the periodic table. How? If the atomic number of an element is known, for example, you can easily identify or determine the number of protons and electrons in the atom. Of course, atomic number is simply defined as the number of protons. So in any atom, we have atomic number equal to number of protons, and is the same as number of electrons. So we have electrons equal to protons. Okay, just as when we talked about the concept of the atom, where we said the number of electrons in any atom is equal to the number of protons, and that makes the atom to be electrically neutral. So if I have an atom, let's take for example sodium. So I have sodium here, which atomic number is 11, meaning the number of electrons in sodium is also equal to 11. And the number of protons is also equal to 11. Now, using our orbital diagram, where a shell is entitled to have a particular number of electrons assigned to it. Now, in that case, we have a total of about 7 shells, indicating the 7 periods in the periodic table. So the first shell, indicated by letter K, has a maximum of 2 electrons, while the second shell, indicated by letter L, has a maximum of 8 electrons. So we can have the atomic structure of sodium written as 2, 8, 1. So indicating that the first shell has 2 electrons, while the second shell has 8 electrons, and the last shell has 1 electron. So taking a look at that, it is clearly shown that the valency of sodium is 1, meaning that is the valence electron present in the outermost shell of the element. Elements in group 1, of which sodium is also an example of an element found in group 1, have valency of 1. Let's look at elements in group 2. A typical example is calcium, where we have calcium, Ca, having an atomic number of 20, which means it is the number 20th element in the periodic table. So the number of electrons is also 20. So if I have an atom of calcium, I can simply represent it as 2, 8, 8, 2, indicating that the first shell has maximum of 2 electrons, the second shell has maximum of 8 electrons, the third shell has maximum of 8 electrons, while the last shell has 2 electrons. So in that case, it is clearly showing that the valency of calcium is 2, which is the valence electrons. Valence electrons are the electrons found in the outermost shell of an element. Now, having talked about that, what happens to group 3 elements? Example, aluminium. Aluminium has a valency of 3, while group 4 elements have valency 4. Common example of group 4 element is the element carbon, with 4 valence electrons. Elements in group 5 have valency of 5 or 3. Elements in group 6, valency of 2. The elements in group 7, valency 1, while the elements in group 8 have no valency. This is simply because they have a complete octet or duplex structure, which makes them inert or non-reactive. They have an outermost shell that is already filled with electrons. Therefore, they don't need to combine with any other atom to form a compound. A common example of group 8 element is the element xenon. Another element in group 8 that has no valency is the element called argon. We also have neon as an example of group 8 elements. All these elements don't have valency because they have a complete octet or duplet structure. Now let's go back to group 1 elements where we said the valency of group 1 element is 1. Talking about group 1 elements. Of course, group 1 elements are commonly referred to as alkaline metal. So, since they are metals, it means they must possess a positive valency or oxidation state. So, the oxidation state of group 1 element is +1. We can generally say that oxidation state is a combination of valency and the charge. So, we have oxidation state, we can have oxidation state as the valency plus the charge. Okay, so we can say metals have positive valency while non-metals have negative valency. A common example of a metal that has a positive valency is the element or is the metal sodium. So sodium can be represented in terms of its oxidation state as +1, written as Na plus, with the 1 not indicated, but it is already shown that it has +1 as its oxidation state. Let's go to group 2 element where we have element like calcium. So we have calcium with symbol Ca. It has 2 plus as its oxidation state or +2 as its oxidation state. In group 3, we have element like aluminium that can be represented as 3 plus, and the valency is 3, while the oxidation state is +3. Which means during ionization, it requires what? To give 3 electrons to become oxidized. While in the case of sodium, it has 1 electron that it undergoes during ionization and gives out that electron to become oxidized. In calcium, it gives out 2 electrons during ionization and become oxidized. Now, in the case of non-metals, where they accept electrons, they have negative valency. So we can simply say the valency or the oxidation state of non-metals or the anions is simply negative. So we have elements like anions such as chlorine with negative valency. So the valency of chlorine is 1, while the oxidation state of chlorine is -1. We also have another radical or ion as hydroxide, represented as OH-. It also has a valency of 1 and oxidation state of -1. We also have another radical or ion called tetraoxosulfate 6 ion, written as SO4 2-. The valency is 2, while the oxidation state is -2. We also have another ion as manganese. So that is called tetraoxomanganate 7. It has a valency of 1, while the oxidation state is -1. So all these are examples of ions and their oxidation states. Having talked about that, the oxidation state of an element or of an atom in a compound can be determined using some set of rules. What are those rules? The first rule has to do with what? a rule that states that the sum of oxidation state of elements in a compound is equal to 0. Or simply put, the sum of oxidation state of elements in a compound is equal to 0. If I have elements in the form of a compound like sodium chloride, the sum of the oxidation state of sodium plus chlorine is equal to 0. So based on this, I can easily determine the oxidation state of sodium in sodium chloride. How do I do about that? I'll simply make sodium the subject of the formula. So I have sodium here as my subject of the formula plus minus 1, which is the oxidation state of chlorine, equal to 0. So I have Na, which is sodium, plus minus 1 equal to 0. Now I have Na plus minus, of course, it will give you minus 1 is equal to 0. So by collecting like terms, I have sodium is equal to 0 plus 1. So Na is equal to plus 1. So showing that the oxidation state of sodium in sodium chloride is plus 1. It is as simple as that. We can also take a look at another element called potassium. In the compound potassium tetraoxosulfate 6. So I have K2SO4 equal to 0. Of course, the sum of the oxidation state of potassium, sulfur, and oxygen in this compound is equal to 0 using that set of rule. So I can have here oxidation state of potassium, of course, it is plus 1. So I have plus 1 multiplied by these two here, plus S, which is the central element, plus minus 2 times 4 to give me 0. So I have here plus 1 multiplied by 2 will give me plus 2 plus S, which is the subject of the formula, plus bracket minus 8 equal to 0. So I have here plus 2 plus S plus minus will give me minus 8 equal to 0. So I have S is equal to, by collecting like terms, I have 0 plus 8 minus 2. So the oxidation state of sulfur in this compound is equal to 0 plus 8, of course, is 8. 8 minus 2 will give us plus 6. So that is why we say the oxidation state of sulfur in K2SO4, which is potassium tetraoxosulfate 6, is equal to plus 6. Of course, the name of the compound is clearly reflecting how the oxidation state of sulfur is calculated in this compound. Having talked about that, we can easily conclude by saying metals have positive oxidation state while non-metals have negative oxidation state. Based on that, we have another set of rules that says that the oxidation state of an element in a free state is equal to 0. So if I have an element in a free state, for example, I have carbon as an element in a free state, the oxidation state of carbon is simply 0. That is very interesting. If I also have another element like sodium in a free state, that is in an uncombined state, the sum of oxidation state or the oxidation state of that element, which is sodium, is equal to 0. So once an element is not combined with any other element, the oxidation state of that element is 0. That is rule number 2. Let's talk about rule number 3. The sum of oxidation state, we are in rule number 3 now. The sum of oxidation state of an ion is equal to the charge on the ion. Let's assume we have an ion as NO3. Okay, NO3, which is trioxonitrate 5 ion. How do you calculate and get the number 5? Of course, the 5 is normally written in parentheses or in Roman numerals. So we have the sum of oxidation state of ions is equal to the what? The charge on the ion. Of course, the charge here indicating what? -1. So you simply make nitrogen the subject of the formula. So here we have N plus -2 multiplied by 3 to give us -1. So we have here N plus bracket -6 is equal to -1. So N plus minus to give us -6 is equal to -1. So by collecting like terms, I will have N is equal to -1 plus 6. Of course, when -6 crosses equality sign, it automatically changes to +6. So we have nitrogen here is equal to +5. So the oxidation state of nitrogen in trioxynitrate 5 is simply +5. Hence, the name is called trioxynitrate 5 ion. It's very simple. Let's take a look at another ion called SO4 2-, which is tetraoxosulfate 6 ion. It is simply equal to the charge, which is -2. So we can have S as the subject of the formula, bracket -2 times 4 equal to -2. So we have S plus bracket -8 to give us -2. So we have here S plus minus, of course, it will give us -8 equal to -2. So by collecting like terms, I have S is equal to -2 plus 8. So S is equal to +6. So the oxidation state of sulfur here is +6. Hence, the name is tetraoxosulfate 6 ion. So that is how the oxidation state of an element in an ion is calculated. Based on this, we can assign these rules in determining the oxidation state of element when they exist in a compound or when they exist as ions. With that, we've come to the end of this class.